All right, first of all, rational. What does rational mean? It means it can be written as a fraction. So if there's rational numbers, there must be a rational function. And if there's a rational function, it looks like that. It's just a simple fraction, 1 over x. That is a parent function we already knew. You recognize it? It's this thing that's graphed right here. Do you remember doing that one before? The blue lines are asymptote lines. I'll move it up and over just a smidge so you can see they're asymptote lines. Remember that one? That's a parent one. Okay. Well, these rational functions, there must be something that's opposite of rational then, which would be what? Irrational. So I want to make a delineation. Here's rationals, and here's irrationals. Rationals are things like 3/4. That can be written as a fraction. It is a fraction. How about the number 7? Why did I put that in the rational side? 7 over 1 is a fraction. Okay. How about like 2.6? Can I write that as a fraction? One big fraction? Yes, I can. Anybody know it in your head? It's 26 over 10. I don't want to spend too much time on that kind of stuff, but that's pretty much everything can be written as a fraction except what? Pi, and there's one other common kind of thing that you can't write as a fraction. Yes, that's true. I'll put that up there. Can't write infinity as a fraction. You can write negative numbers as fractions. Like -6, that's just -6 over 1. Thank you for trying, though. What else you got? Square root of 1, that's the same thing as exactly as 1, and therefore it's rational. There you go. Square root of 2. Does it have to be square root of 2? No. Could be square root of 3. Could be square root of 7. Any square root that doesn't work out nice, because if it's a square root of something like 1, or square root of 36, and it works out nice, then it would be rational. So there's only a few irrationals, and there's like a bazillion rationals. Well, that's actually not true, because there's an unlimited number of square roots like this. So technically, there's an infinite number of irrational numbers. How do you say that there's more rationals if there's an infinite number of rationals and there's an infinite number of irrationals? Isn't that kind of weird? And yet, almost all the numbers we work with, that's a safe statement, are rational. All right. So it's important to have that rational function. Now, one number that kind of messes with people is like a repeating decimal. It's a decimal, but yet it's weird because it keeps going on forever. Should 0.8 repeating go on the irrational or the rational side? Because why? It can be written as 8/9. Very good. So 0.8 repeating was 8/9. I'm going to put that over here on the rational side because it can be written as a fraction. So here's my question for you. 0.9 repeating. Where should that go? Rational or irrational? Tell me what you think. Do you get that it has to do with rational and irrational because it has to do with, can you write it as a fraction? So can you write 0.9 repeating as a fraction? All right, how about this? Obviously, the thing it's really, really close to is what? 1. Does anybody think it goes so far as that 0.9 repeating is actually equal to 1? It's the same exact thing. I think it's just a teeny tiny bit less than 1. All right. I want you to have to take a stand on this. 0.9 repeating, is it 1 or is it less than 1? All right. So here's the stand I'm going to make you take. I want you to actually stand up. We're going to have sides of the room, and then you're going to argue with each other. There'll probably only a few people on one side that shouldn't make you scared. Okay? You should just go wherever you think is right. And the quality of your argument is what I want to judge. And just having an argument at all is better than a lot of kids who won't be able to articulate anything. All right, so you have to decide. Do you think 0.9 repeating is equal to 1 and therefore rational? Or do you think 0.9 repeating is not equal to 1? If you think 0.9 repeating is equal to 1, you're going to be on this side of the room. If you think 0.9 repeating is not equal to 1, you're going to be on that side of the room. Okay, go. Get up. I don't want anybody sitting in their seat because it's not fair to the people who moved. Excuse me. The fish is the dividing line. If you're on one side of the fish or the other side of the fish. All right. Now, what should win the day is not just who has the most numbers, but who has the best argument. So, somebody want to make the case for this side of the room, which is the, you guys are saying that 0.9 repeating is not the same as 1. Go ahead. Hey, don't talk.
Keep going on forever. Like say that like 9/10 is close to that. Keep getting closer to that. Keep adding numbers like 10 over 11, 11 over 12, and it would go on forever. But you would never get that last number. It would always be that close.
So you're saying it's really, really close, but it's not. All right. You guys must have a reason you're over here. What do you think? Quiet, please. Listen. Hold on. 1/3 equals 0.3 repeating, right? I think you'd all agree with that. Okay, go ahead. Are you saying to add these together?
Yeah, add them together.
Well, isn't that interesting? I added up the left side, I added up the right side. 0.9 repeating is equal to 3 over 3.
And also, it's literally impossible to get closer to 1.
Okay, that statement was it's impossible to get closer to 1 than 0.9 repeating. 0.9 repeating is as close as possible to 1, but are you saying it's actually different than 1 then? Okay. Anybody want to use that same argument against him? Go ahead, say it. One of you guys back there, use that same argument against him then. Oh, come on. Yes.
Well, you said it's impossible to get closer to 1. You can say it's like impossible to get it's impossible to get closer to 1 than 1. He's a traitor. He's not on our side. It's impossible to get closer to 1 than 1. Oh, but, well,
all right.
But if you're saying that, that's 1 minus 4 times, you always get 0, 0, 0, 0, 0, 1. They would go on forever. Yeah, you want 1 minus 1.
So the next argument was somebody said, this is how close it is to 1. And then the other side of the argument was, no, you'd have to keep going forever, right? That's what repeating means, right? So if you can't tell how far apart it is from 1. All right, I have another math bomb to drop that I think will make some of you think about your positions. Rational numbers can be written as a fraction. All repeating decimals are rational. True statement. I'm telling you, that's a math truth. All repeating decimals are rational. All right. So now, anybody want to switch sides? Yes, sir. Gotta be able to hear. Go ahead, Seth. 0.9 repeating can be written as a fraction, I think you mean.
But then, like I said before, no matter like how big of a number over how big of a number over, you would never get that. It would always be rounded. Oh, I got this. There would always be like an 8 at the end.
There's another argument for your side. There's another argument for your side, and it has to do with the ninths. Can you give me an argument based on the do you know what 1/9 is? So you gave a pretty good argument before. All right, I'm losing about a lot of the class. They can't apparently handle standing next to each other without talking. So I know who they are. It's not most of you, and I appreciate most of you being quiet. Okay, Mr. M, you're going to meet me up at the front desk. Everybody else have a seat, please, in your normal seats. All right, so I want you to decide tonight whether you changed your mind or not. I know it's tough to in the middle of class where there's a whole bunch of people and they're going to be like, no, you can't leave our side. But you have to decide for yourself let's do that last argument that I was trying to get to, and all of a sudden the craziness with the broken iPad happened. Let's 0.7 repeating. What's 0.8 repeating? So what's 0.9 repeating? Oh, interesting. Yes, sir.
So, like, just say that, but then with every answer that's 1, it's actually 0.9 repeating and it's rounded.
So is this just a rounding thing? Is this just a rounding thing? Well, is this a rounding thing?
No, like if you're saying I'm saying maybe like everything that's 1 is actually 0.9 repeating rounded to 1.
I gotcha. So is 1 really not ever exist? There was only 0.9 repeating. That's a harder way to think about it, but if 0.9 repeating is exactly the same thing as 1, then what you're saying is true. All right. So you have to decide for yourself whether 0.9 repeating is rational or not. I already actually told you that it's rational, but then if it is, then you must have to rearrange how you're thinking about 1. All right, we need to move on. I want to go to this slide right here and show you the parent graph, except it's been moved. All right. Parent graph is this, 1 over x, except it's been moved. Which way did it get moved? Left 1 and what? Up 4. Those are just like you expect them to be. Sorry, down 4. So I'm going to pull out under my pictures. I've got this one somewhere already graphed because it takes forever to graph it nicely. Oh, rats. Okay, it was in there before. For some reason, I can't find it right now. I will do it quickly by hand. This spot and this spot are the key points you have to be able to graph to do this parent function. And then it's like this, and that's close enough. You do like to have an asymptote lines in there, but I'm not going to draw them because they're too hard to move. All right, so now I got to move this thing 1 to the left. I'm moving everything 1 to the left. Taking this little red dot and moving it 1 to the left. Taking this other little red dot. Okay, I got to do it with the mouse. And moving it 1 to the left. Come on. There. Okay. So now, that's my new graph. And the domain, this is important. Oh, I haven't moved it down 4. Thank you. Gonna grab everything, move it down 1, 2, 3, 4. And I gotta move those points down 4. There. Okay, now, there's the graph. Thank you for catching me on that. Where is its vertical asymptote? That's this dotted line right here. And that's at x equals -1. Where's its horizontal asymptote? Horizontal is like horizon. That's right there, and that's at -4. And that's at y equals -4. It's really easy to confuse your x and your y for the verticals and the horizontals, and so I'm going to start saying something that'll help you remember it. Just like I said, order patterns. Do you still remember that? And that had to do with the p went with order matters. Permutations, order matters. This one, vertical, I'm going to say it's the zertical asymptotes, because that'll remind you they're the x ones. Because you know why? So often I had to mark them wrong because the kids would write y equals -1 for the verticals. Hopefully this will help remind you. And then take a while to guess what I'm going to call the horizontals. The horizontals, very good. The horizontals and the zerticals. So the horizontals are the y equals things. All right, if I move down to this, if you can factor something, you should. I've told you that before. And this on the top, that can be factored. So therefore, you should factor it. Everybody, factor that quickly. If you aren't on this screen, get there quickly and factor that. Two sets of parens. X and X. Who's got it? -4 plus 3. Good. Now, do you remember one of these on the top 20 sheet or one thing just like it? Now what happens? F plus 3 cancels. But what you never were told before is that makes something funky on your graph. That makes something called a hole in the graph. The function will be running along at whatever's left here. After those cancel, this is the resulting function is what I call it. Y equals x minus 4. Do you know what that graph looks like? It's got a y-intercept of -4, and it has a slope of 1, and it's just like that. It's a line like that. And it's got an empty spot right at whatever would make this crash. Do you get how -3 was the thing that would make the bottom 0? And therefore would make it crash. And so at -3, 3 spots over, there's an empty spot on this graph. So I'm going to just make it keep going a little further and have an empty spot right there. That, I'm going to actually make a little empty place for it. That is a graph that has a hole in it. It has an empty spot right in the middle of it. And that empty spot is at the thing that would crash the graph. If you put in a -3, this whole graph crashes. Why? Because, look, put a -3 right there. There's a 0 on the bottom. It doesn't matter what's on the top. The thing crashed. So if you put in x is -3, that's like this, and you follow it down to where there should be something, there won't be anything. All right. Now I'm going to show you how to do domains. The domain is pretty simple. Everything works except. That's how you always start saying a domain. So everything works except what? -3. And here's how you say that. All real numbers except x cannot be 3. And to make this official, this is the true mathematical way to say it. X is an element of the reals, comma, and x cannot be 3. Write that down. It's going to take you a while before you get that all straight. Your test on this stuff is coming on Friday. And I've already taught you about half the stuff that you need to know. Nope. Oh, yes, it's -3. Sorry, you're right. It can't be -3. Because if I put in a 3, that doesn't make it crash, does it? Good catch. Thank you. -3. X is an element of the real numbers, and x cannot be -3. What that means is all real numbers work, except x cannot be -3. All right, vertical asymptotes. The verticals are the zerticals. So do you know that this is an x equals thing? The next thing is your vertical asymptotes, they come from whatever would make this thing crash. Whatever would make this thing crash is either going to be a vertical or it's going to be a hole, one or the other. Since there's only one thing that makes this thing crash, and that one thing that makes this thing crash is a hole, because there was something on top that was just like it. Remember, it was like this? Since that canceled that, there was one on top, one on the bottom. That creates a hole, not an asymptote. So there is no asymptote. But there is a hole. And the hole is at x equals -3. But then if x is -3, the hole is a place. Remember on the graph, it's like an empty spot? That's a place, like an x and a y. So you can't write it like that. That's the baby way of writing it. We used to do that, but we've grown up now, and we make you write it the real way. A hole is a place, something, comma, something. -3, comma, something. And how do you know where the other spot is? You take the -3, you stick it into the resulting equation, which was y equals x minus 4. After this thing canceled, that's what I had left. And I take that negative 3, and I know x is negative 3. So I stick in negative 3 right there for the x. And the y must be negative 3 minus 4 makes negative 7. I know it's a lot to absorb, but that's what you need to learn for today, and that's half of the stuff you need to know for test. In fact, it's 3/4 of the stuff. Okay, so I don't expect you to be perfect at this yet. Just showed you the first one all the way. Okay, still have a question or answered? Okay. All right, this one. Remember, if you can factor it, you should. Go ahead. Factor that thing. Stay with me. Factor it. Thank you. And once you cancel those two, which I hope you already noticed, you should write the resulting function. Y equals x plus 2. That is a line. It's a line that has a y-intercept of 2 and a slope of 1. So basically it would look like this. That's a line. Except it's a line that has a what in it? A hole, and the hole is at 2. That's where x is 2. So I'm going to go over 2 spots and go up here, and there'd be an empty spot right there. That's how the graph would look, just so you know. Nope, because is 2 or negative 2 that causes the problem? It's 2. Plain 2. Okay. I know that can be confusing. I got the last one wrong, but I got this one right. So 2 is the problem, not negative 2 this time. All right, so now domain. Remember how to write that? X is an element of the reals, and x cannot be 2. 2 is the only thing that crashes this. Oops, I forgot the x. Now the verticals. The vertical asymptotes are these vertical asymptotes. X equals, and remember, it's either a hole or an asymptote. There's only one thing here that's causing a problem. 2. Is it an asymptote or a hole? It's a hole, so it's not an asymptote. I say none on the asymptotes. And the holes, it's 2, comma something. Yep, because this x just goes into this little equation right there and tells me the y. 2 plus 2, y must be 4, 2 comma 4. Raise your hand if you think you can get an easy one like this right now. Okay, good. Now we'll step it up to ones that are a little harder. That one you can factor by grouping. Try number 4. Do a factor by grouping thing. Something will cancel. See if you can get this whole thing right without me. It's a little harder because it involves factor by grouping, but it's not like really hard. If nothing cancels, then that thing's an asymptote, not a hole. So it depends if something cancels or not. In a few minutes, I'll be giving you your test back. If you aren't able to factor this, then you probably didn't do too well on your test, because it was all about factoring like this. If you've been in my class since the beginning of the year, you know I've told you factoring is like the number one thing that we got to get you good at this year, because it comes up so often. Here it is again. All right, this and that can be grouped. So then x squared comes out of this one, and what I have left is x plus 3. And negative 1, it's kind of weird, but negative 1 comes out of that one. And what do I have left? X plus 3 again. Yay! Since that and that are the same, that factors to x plus 3. And then the leftovers is right here, x squared minus 1. And if you just wrote it like that, you might have done that on the test also. That's not factored all the way, and therefore you lost the point. X squared minus 1 breaks into x plus 1 and x minus 1. And that's all over x plus 2. Does anything cancel? Therefore, there is no hole. None. How do I do those domains again? X is an element of the real numbers. You put a double vertical line on the real. The R, I don't know if you've noticed that, but I've always been doing that. That's the official sign for real numbers. If you look it up on Google and Google the image for the real number symbol, it's a R with a double line right there. Anyway, All real numbers except x cannot be what? -2. And if that thing wasn't a whole, then it must be a vertical asymptote. And notice I take the not equals off of it. Very common mistake. People think that it's the not equal sign. It's a line at -2. It's a line. It's not a thing it can't be. It's a line. And if it's a line, it has to be an equals. And if you say a y by accident, I'll have to go off on you. That x, the verticals, are x equals things. If you call them y equals things, then you just made it equal like this. And that's totally a different thing. All right. All that happens is they get harder to factor. That's all. And after that, it's the same exact thing. I'm going to do this one in speed mode. X comes out of everything here. X comes out, and I have x squared minus 2x minus 15. And then it'll factor again. In the bottom, x comes out, x plus 5. And then the top, this part here factors, and I bet you anything there's an x plus 5 in it, right? Because that'll make this bottom thing cancel. But I'm not sure, so I'm going to try it. X plus 5, and then say x minus 3. Wait a minute, that doesn't work. It has to be minus 5 and plus 3. And that means those 5s will not cancel. They're setting up to see if you would get suckered into canceling those out. But they don't. But what does? X does. So since that's the thing that canceled out, that makes the whole. Now we can do the rest of the problem. Domain. Oh wait, I should write the resulting function. The resulting function was y equals x minus 5 on top and an x plus 3 on top. None of that canceled. This is all the stuff that's left after I canceled. There's my resulting function. Okay, the domain. X is an element of the reals. And x cannot be, what? -5. Anything else? Yeah, a lot of people get that one wrong. What else can x not be? Yes, look right there. See how there's two things that would make it cancel? 0 and -5. X also cannot be 0. Now, you remember how I was saying that things are either a whole or an asymptote? They can't be both. It's one or the other. This time we got one of each. This time we got one of each because this one made a whole. So which one was the whole? The 0 or the 5? The 0. So this is a vertical, and I'm doing the holes right now. The whole is something comma something, and it's 0 comma something. And then you remember how to find the other part of it? Stick it in. 0 goes here, here, here. -5 times 3 is -15 over 5. What's -15 over 5 simplified to? -3. 0 comma -3 is where the whole would be. And the last thing, vertical asymptotes. Vertical asymptotes. Vertical asymptotes. That means it's an x equals thing. And that reminds me it must be one of these two things. And therefore, what is it? -5. Raise your hand if you would have had that one right. Okay, good. All right. Now, that's all examples I have. Remember, factor it. See what cancels. So I'm going to leave an answer up here just so you can see how you should write that whole x element of the reals, blah, blah, blah. Okay? And your homework for today is a little bit long, so I'm going to allow you to skip problems, let me see, 4, 5, and 6 on the front page. 4, 5, and 6. 1, 2, and 3 are really pretty easy. You can skip problems 4, 5, and 6. Yes, you do have to do 7 through 12. 1, 2, and 3 should be like super quick and easy though. Like literally, I would suggest 3 minutes is all you would need if you understood what just happened there. So the real part of your homework is 7 through 12. 1, 2, and 3 are like warm-ups. You're assigned them, but that should be quick and easy. All right. So that's all I have for the video for today.